I'd like to introduce you to Rachel Beckett. If she's not the largest person on your screen at the moment in terms of monitor size, then please select and she'll talk to you. She's St John's, 1985, and a graduate in the history of art. And she's put together what I think you're going to find is an absolutely intriguing study of our perception of colour. And so, just a minute, we've got more people joining by the minute. Yes, I'll very shortly hand over to her. Just waiting for one or two more people to come in. Yes, I think we can start. Rachel, good evening, welcome, and we're all looking forward to hearing what you have to tell us about colour.
Right, thank you, Mike, and hello everyone. And I'm going to cut straight to the chase, I think, because we're sort of fairly time limited. So I'm just going to share my screen and we'll get started. Thank you for joining us. So, Mike, I think you need to allow me to share my screen. It's saying host disabled, attendee screen share. We had that before, didn't we?
Yes, just one moment. To apologise, where's that setting gone?
We did say there might be a technical hitch.
Yep.
Was it to do with whether people were, no, it wasn't to do with muting, was it? Because I'm not muted.
There you go. I think that's it.
Let's try again then. That's looking good. There we go. That looks good, doesn't it? Right, so let's just get to my first slide. Okay. So as you know, the title of my talk is Are the Primary Colours Personal? So I'm just going to talk a little bit about the spectrum first. So as we know, Sir Isaac Newton discovered that white light could be split into a spectrum of colours. You can see my nice spectrum here on my lamp. It's quite hard to capture a photo of it, so I was quite pleased with that one. And I've often had conversations with people about colour and picked up that we might not all be seeing the same colours. Now, Isaac Newton identified 7, he just named 7 colours in the spectrum, but of course we could give them all sorts of different names, and as we know, we can see many colours. I've got some examples here of disagreements about colour. So for example, the little rhyme, roses are red, violets are blue. I always thought, well, why would you have the word violet if violets are blue? So there's clearly some disagreements over purples, violets, words like that. Also, with the word red, I've noticed a lot of wildflowers, and here's the familiar robin, they've got the word red in their names, and they're not what we might think of as red. But by the way, if I say anything about colour and you disagree, feel free to use the chat, because my argument is that colours are personal, and if they are, you might be seeing something slightly different. So that's fine. Be interesting to talk about that at the end. So the red dead nettle looks a bit pinky purple to me, and the robin looks quite an orangey red to me. So I was interested in, is there something going on here that we can actually define? And in the rainbow, I should say, the violet looks very bright and vibrant to me, and that's always been an issue where I've disagreed with some of the people. So I started finding out about the facts of colour vision, and I apologise to anyone who knows about some of these first few slides already, but it's good to cover this. So the human eye sees colour through 3 different types of cone in our retina, which are specialised cells, and they've got photopsins in them, which help us see red, green and blue. And here I've done a chart of how we see the red, green and blue in terms of where they are in the electromagnetic spectrum. So the visible spectrum runs from 400 to 7 700 nanometers, nanometers being 1/1,000,000 of a millimeter, so very, very tiny wavelengths. And we have these specialized cells to see red at roughly 565 nanometers, green at roughly 546, and blue violet at 440. And this the vertical axis just shows how good the extent to which the cones are picking up to their maximum capacity, the amount of coloured light that's available. You can see here from the inset that actually, because the violet light is very much stronger in terms of energy, the blue cone doesn't have to be doesn't have to pick up so much light to give the same effect, because it's such a strong energy. Sorry, I didn't explain that very well, but hopefully you get the point. And this diagram here, I'm not going to say very much about it. It's an international system for measuring colour according to 3 parameters. So you've got your sort of spectral colour, your saturation, and your luminance, but that's not really going to be the focus of my discussion. I'm thinking more about the way the eye, the way the 3 cones operate, the 3 types of cone operate. So here I've got some diagrams you might be familiar with. The standard primary colour diagram here, top left, shows how a computer models the red, green and blue by lamps that are coloured red, green and blue in the screen. And it uses what's known as the hex code for colours. So it's base 16, and it goes from 0 to 255 is 256 minus 1, because you've got the 0 in there, which is 16 squared. So the maximum value you can have for any of red, green or blue is 255. So you can see the red will be 255 and 0 for the other 2. Likewise, blue is 255 for blue and 0 for the other 2. But you can also see that the mixes are the secondary colours. So for magenta, you've got blue and red on maximum. For yellow, you've got red and green on maximum, and so on. And you'll also notice that the primary colours of your inkjet printer, also the primary colours of paint and art and so on, are these secondaries up here. So the cyan, magenta and yellow work in reverse in paints and inks. So you mix the cyan and yellow to make green and so on. Cyan and magenta make this blue colour. But still violet is missing, and that is a bafflement to me, and these diagrams have never quite worked for me. I've always thought, well, where does violet fit in? Because it doesn't look to me like it's just a mix of magenta and dark blue, which would give you a sort of darkish purple. And then orange is the other one that's missing, although of course that's between the red and the yellow. But you can see here on the right from how our cones work, that we're making colours by the cones firing in groups. So yellow is when the red and the green cone are firing together, for example, or they're absorbing the light together. So this shade of mid-blue would be when the blue and the green cone are absorbing light. So you can see a lot of the colours we see are 2-dimensional in this way, being picked up by more than one cone. And strangely enough, the peak of the red cone, the peak absorbency, is where we're seeing yellow, because we're using the green cone as well. So as you use less of the green cone, you get orange, and when you use really only the red cone itself, that's when you're seeing red. Conversely, at the other end, when the other cones stop firing, all you're left with is violet. So this is why I was tending towards violet, as wanting violet as a primary colour in my own system. So anyway, as a painter, I had been frustrated with primary colours I'd been given at school. Of course, they give you red, blue and yellow at school, which is even less logical. They don't give you magenta, cyan and yellow, which are better. But I still found that if I mixed magenta and blue, I got a darker purple. I wanted a brighter violet, so I started using that as my 4th colour. And you can see here one example of some art that's sort of based around that kind of colour scheme. So you can see I've got some greeny yellows or yellowy greens, and I've got some sort of cyan type colours and so on. And by the way, it's a Penrose tessellation, if anyone's interested, or I can talk about that another time. But that's an example of, in my painting work, how I might use primary colours. I also, as a printmaker, was printing in different colours, and I thought I'll explore. I tried a different set of 4. This time I couldn't get a light, bright violet, so I thought, well, I won't use violet, I'll go back to blue. I chose this sort of nice mid blue, a pinky red, already pink, a bit similar to magenta, and then a sort of golden yellow and a bright green. So as you can see, I got this result. I did actually a print where it's one block and it's different in each corner, and you can rotate it and print it in each colour. So you print it 4 times in different colours. And it gave me a very nice, I think, nice chromatic balance and also tonal balance. But obviously you can't get yellow if you're mixing those colours. This colour in here, I've digitally mixed them here. I think if I know that if I brighten that up, that would become a yellow. But obviously I'd need lights to do that. So in my artwork, I didn't have a bright yellow, but that was fine because I knew I wasn't going to. But it was an interesting experiment. Anyway, some while after this, I found out about a fascinating study by these authors, Jordan, Deep, Boston and Mollon, on the gene for red-green colour blindness, which is, as you know, very common. It tends to be men who suffer from red-green colour blindness, and this is because the gene that causes it is on the X chromosome, which men only have 1 of and women have 2 of. And it's very close to the genes for red and green perception, which are also on the X chromosome. So all those 3 genes are on there. So what often happens is a person, often a male, receives this gene for perceiving either green or red in a different place on the spectrum. So what happens is they get a slightly different photopigment in their cone in their retina, and they get what's called trichromatic vision with an anomaly, so either deuteranomalous or protoanomalous trichromatic vision it's called. So there's one, this type in the middle is commoner, that's where your green is a bit closer to the red, but the protoanomalous type is where the red is a bit closer to the green. So you can see there's going to be a bit of confusion over yellows, buffs, peachy browns and things like that in there. But what this study found was that the women who carried the gene and passed it on to their sons, because they studied about 32 pairs of women and their sons, these women sort of had perfectly good colour vision, but potentially they could have the photoopsin for a 4th colour. Now they tested all these groups of people, and actually they did find 1 woman, but only 1 woman who could see orange as a 4th primary colour here. So that was very interesting, and I was interested in this. I thought, I wonder if I'm one of these people. So I started exploring and testing my own colour vision and also my children's colour vision. They were quite happy to go along with it. I've got a son and a daughter. So we used these Ishihara colour plates, which you may be familiar with from having been tested at school. And I tested our vision. Obviously it wasn't totally scientific because I was doing it, but I tried to do it as fairly as possible. And it did turn out that my son is slightly red-green colourblind. Meanwhile, my daughter and I were perfectly able to read all the plates, although I could see there were some strange colours in there, and I could see why someone might not read them correctly. So again, obviously this is on my screen, so the colour, you know, it's all relative to what screen you're using. You'll be seeing it on your screen, so it's only as good as the quality of the screen. But so anyway, I thought something, you know, I might possibly be in this group that was studied by Jordan, Mollon et al. So I went on with my investigations. I visited the University of Bath physics department, and they have a machine there called a monochromator where they can show you individual wavelengths. So we had a look at that, which was fascinating. We managed to agree on where yellow was, 580 nanometers, and we had a look at violet. And I seemed to be seeing a slightly brighter shade of violet than they were, which was interesting. And then when they projected this spectrum for me, I didn't see it as completely symmetrical. There seemed to be a sort of bulge at the violet end, which I thought maybe suggested that I wanted a bit more spectrum in there. It's just my personal reaction. But anyway, I thought, well, there might be something going on with me seeing a bit more violet or something. So I went to, I contacted John Mollon at the University of Cambridge as well, and he very kindly did the tests on me that he'd done in his study. This was from my memory, what his primary colours look like, and this orange would belong in here somewhere. So my son and I did the tests. He agreed that there was probably a colour blindness gene at play here, but I did not test for the specific orange perception that he was looking for. So that was fine, but you know, only one person in the world had so far been found to have it, so that didn't exactly surprise me. But I thought, well, something is probably going on here. I want to find out what it is. So I started thinking, what are the purest colours that I ever come across in my own experience? And I started thinking like wildflowers, the brightness of wildflowers. And again, if you disagree with me, put something in the chat. But to me, the purest, brightest colours I see are, you know, the colours of certain wildflowers. And so I started taking photographs and trying to adjust them to make them more like I see them, because this photograph here didn't give me as much chromatic contrast as I wanted. So I've got this early purple orchid here, and I've brightened it up by only the orchid. You know, I left the background different and did something different with the background. And then the cowslips here, again, I've done something different again to get them right. Now at the bottom, you can see a breakdown of something I did with a different plant, the green alkanet, which it's odd it's called green, because to me the blue is the perfect shade of blue. I wonder if it's been seen as a pivotal colour before by researchers. But anyway, on the left here you see the photo that my phone took, and again, for a proper study I probably need to do a technical note of what the phone is, but anyway, it wasn't accurate to what I was seeing, so I amended the photo to make the flowers the right colour, and I got this image on the right, which obviously has got a lot of redness in the leaves, and then I copied the flowers across. So I thought, well, there's something going on that's a bit odd here. My colour separations seem to be a bit different from what's expected. So I then decided to build a whole spectrum with sort of benchmarked against plants, because with plants, you know, you can name the species, you can, it's a consistent thing, you know, apart from slight variations in soil and light, it's always going to be the same. So I built up a spectrum. This isn't the latest version actually, because there are reds on it as well now, and I've added things, but I used a Royal Horticultural Society chart to actually identify the colours of the flowers that way. I then also did digital models of them on my, obviously it's a 3-colour screen, it's an iMac I'm using, so it is subject to the restraints of my iMac, but it does have good colour quality. So they're models for these colours, but I've listed them all, and here on the left you can see some examples. The Aubritia Royal Violet, it's the only one that's not a wildflower, but actually I've got some of them here, I'll show you afterwards, but it just is such a vibrant violet to me that I wanted that in there. Then I've got this colour here, which we might talk about at the end, but just suffice it to say the Japanese have a word aoi, which means blue-green, and I'm calling it copper hydroxide, which was my natural benchmark for it. I couldn't find a plant with that colour. Then here, this one's quite interesting, the beech. I thought, well, the brightest green is the green of light shining on young leaves. So I took this photo of young leaves, I colour picked the brightest bit of it, and I got this colour here, which again we might discuss at the end, but to me that's really a yellow when I see it in isolation. And then finally the marigold, very vibrant orange, is a colour that's of interest to me. So really I built up all the colours that look very pure and primary to me in some sense. I'm not saying they're all primary, but they look like spectral colours, and I thought my primaries should be chosen from among these. So just a note on technical matters next. So to mix these colours, I used digital mixes. So I put my 3 red, green and blue values from my benchmarked colours into a spreadsheet I designed, where I can basically average them. So for example, here I've got a violet and a red, and I can average the red, the green and the blue values to get a magenta type colour in between. But I wanted to put this up because Photoshop actually thinks these colours are equivalent. I haven't worked out quite what it does, but sometimes it'll change the colours. I need to look into this. But it still reckons that that recipe for the colour I've got there is the same in both examples, whereas to me, this one is very bright spectrum colour, and this one is a much darker sort of bluish purple. But you can see from the grayscale there that they look very much more similar in brightness according to the grayscale, but not to me up here. But again, if you've got thoughts on that, put them in the chat and we'll hopefully have a chance to discuss them afterwards. So anyway, I'd been told I wasn't seeing orange as a fourth primary colour, so I thought, well, I'll stick with 3, but I need to adjust them to be right for my vision. Now, top left was my sketch of how I thought it might look, a sort of violet, a bluey green, and an orangey colour. And I thought, well, if you brightened them up, they might look like these colours here. So I started playing around, and I've actually done hundreds and hundreds of these digitally mixed experiments, but I've picked out the ones that seem most useful to show you. So I thought, well, I'm going to have a violet because violet is at the end of the spectrum and it looks primary to me, and that's sort of fundamental to what I'm exploring. So I've got a violet, I've got a warm red modelled on a strawberry, which to me is the sort of reddest of reds. And then I've chosen a mid-green, which I've called beach, but it was more conceptual. It was me trying to mimic a green I found on an online colour picker, which was specifying this is what the green at the peak sensitivity of the green cone would look like. And I've tried to find a sort of natural match for that, but because the one online looked too synthetic, I wanted something that looks like a colour I might see in real life. But anyway, that one didn't work too well. You know, I've got the purplish early purple orchid colour in here, but I've got confusing buffs and greys. It just didn't feel right. So I tried another one with my copper hydroxide colour here, and that was very, very pleasing. I got this, what seems to me a lovely mid-blue here, the colour of the green alkanet flower. And because there's a wide gap between these two colours, the red and this one, the copper hydroxide, are virtually complementary. I've actually, interestingly, ended up with a really neutral grey in here, so it feels like something's missing. So I tried a more yellowy colour, which was supposedly green because I got it from my photo of the green beech leaves, but of course it's very yellowish. Again, if you disagree, let me know. But this time I got a lovely orange. I got a narrower gap between the red and this greeny yellow, and I've got my sort of marigold orange in here. I've got my royal violet colour here, but this time I've got a sort of rather strange buff colour on this side. So it just made me think I need 4, you know, to plug both those gaps. So I started trying out what I could do with 4. And again, I've done loads and loads of different variants to try and see what works. But I thought in the end, the best match were these ones that we were looking at on the last slide. So the blue-green opposite the red and the yellowy colour opposite the violet, which are basically complementary colours. And I mixed them and got this very pleasing result, to me, very pleasing result. So you can see, again, they're digital mixes, so they are actual on-screen mixes of these colours averaged out. And all the pairs are complementary, as in, I mean, they look complementary, not mathematically, but again, it's a model of what actual lights might do if you had 4 pure spectral lights. And I'm modeling this in 3 lights, so the numbers aren't necessarily going to quite work, but they look complementary, as in opposite inverse colours. And you can see in the middle of this right-hand diagram, I've superimposed my primary colours I used for my lino cut, and they match the secondaries of these notional 4 mixed lights very well. So the green, the orange and the blue match very well, and even the magenta. I think if you lightened up this early purple orchid type colour here and brightened it, it would be quite similar to this. So that was very interesting to me indeed, and looked very satisfactory to me. We haven't got too much more to say now, but yes, so looking at this diagram from the previous slide, what was very interesting to me was all the colours looked like real colours that I see in the environment, rather than the synthetic ones that are only seen on screen or in manufactured plastics or something. So I've tried to match them. The green, I didn't think it was a leaf green or a plant green at all, so I've matched it to this insect called the shield bug, which some people might be familiar with. But I've, you know, they all feel to me like specific colours. I've got the colour of purple sprouting broccoli in there. So I felt it was working for me. And so I then did another experiment in Photoshop where I basically had a layer for each of these 4 colours I decided to use as my primaries, and try and build up a rainbow from them. And I've only used those 4 colours to make this, and it does look to me very much like what I see when I see a rainbow. So I feel quite satisfied that for me, those are my, if you like, my 4 primary colours that work for me. But to prove it, I would need to see them done with lights, which I haven't done yet. So that'll be a next stage of my investigation. So I just wanted to draw the thoughts together a little bit. Hopefully I've just got time, Mike. Anyway, I'm just going to quickly do that.
To go.
Okay, I'll do my best. So I discovered this diagram showing how the rods function, which are the cells in the eye that don't see colour but see black and white, and we use them at night. But very interestingly, they absorb very strongly in the blue-green area of the spectrum. So I thought, well, what if my rods, along with all other people whose vision is similar to mine, are actually seeing some colour as well? And if they were, it would look like this, with the rods absorbing colour in this area. Also, I found out, I've not got time to tell you much about it, but the red cone also does absorb in the violet area of the spectrum as well. So all that being so, you could get a multi-dimensional colour vision here, with each colour composed of at least 3 rather than 2 components, which would give you a much richer colour vision. And you'd see interesting browns and blues because of this multi-dimensional quality to the colours. And so finally, if I've just got time, I want to tell you about the conjectures I came up with as a result of this. So basically, what I've just told you about is the first conjecture, that the rhodopsin in the rods might be seeing some blue-green in certain people's vision, including mine, which would give you more differentiated violets and blues. Or alternatively, as in the Jordan and Malone et al. Study, if I've got the colour blindness gene, I might be seeing a slightly shifted green in the red direction, but also my green cone might have shifted its perception more in the blue-green direction, so that instead of seeing green somewhere here, I'm seeing it more towards the 496 nanometer area, which is where my copper hydroxide colour falls on the spectrum. So those would be conjectures that a scientist would have to pick up from me and explore in, you know, more perhaps specifically scientific ways. But I think for me, those are conjectures which describe the anomalies, if you like, in my own colour vision that I've been thinking about for so long. So that's basically it. I've got some references and I think I'm out of time, but we can go back to those if anyone wants to see them. And finally, I don't know whether we will have time, but it was a little quiz for you to tell me what colour you think this is. It did feature earlier in my talk. And which of these 3 colours you think is the one at the end of the rainbow, basically. So that's my talk. So shall I leave that up there for a minute, Mike, or what shall we do? I don't know if people want to...
There aren't any questions there at the moment, so if you wanted to carry on for a few more minutes, we can use the Q&A time to do that.
Yeah, okay. Well, I mean, if anyone who is listening and would like to have a go, would want to answer my 2 questions in the chat, that would be interesting. I mean, there are no right or wrong answers. This is about, I mean, you know, trying to find out how your vision might be the same as mine or differ from mine. But obviously, you're looking on your screen. I'm using my screen. It's not totally scientific, but so if you think the top colour is blue, you can put a B in the chat. If you think it's green, you can put a G. If you think it's neither, an N. And then with the 3 violets, choose Y, sort of X, Y, or Z as the colour that you see at the end of a rainbow. Obviously, you'll have to remember what you see at the end of a rainbow when you see one. And I've suggested if you're using an Apple product which has different and rather good colour differentiation, you might like to add an A at the end as well, or just write Apple. And then I don't know if Mike and I will be able to look at what answers we get.
You're getting the, if you look at the chat, you can see the answers coming in.
I stop sharing now and come back. Does anyone, I can't ask if anyone wants another minute on this. I'll just give it another couple of seconds for people to finish, and then I'll stop sharing and come back and look at the chat. I think that should do. Right, I'm going to do 3, 2, 1. Right. Okay, thank you everyone for listening. So let's just see. I wonder if I'm going to be able to save this chat for later so I can look at it properly.
Yes, we can save the chat. And I think
good. Well, I might do that later rather than try and analyse it now, but it looks like I'm getting some slightly differing answers there, which is
like some fairly diverse answers. Yes.
Yes. If anyone wants to see the slide again, let us know, and you know, we can go back to it. But also, it's going to be uploaded, isn't it, into our onto our website?
Yeah, so once the video's been processed, we can upload it to our YouTube site, and I'll put.
And also my presentation will be on there if anyone wants to, you know, look at the slide again. Or, I mean, I'd be very, very interested if anyone has got, you know, thoughts to communicate to me. So my email address is on the last but one slide as well. So what I'd quite like to do is actually then set up some experiments to compare my vision with other people's, because obviously this was a self-evaluation based on my own vision. So the next thing is to find how that compares to, you know, other people's, maybe a control group, and then people who think that they might have, you know, the colour blindness gene or something like that. But that would be a next stage, really. So yeah, if anyone has a question, I don't know if there are any in the chat. Hold on. What about parental influence? Someone said. Yes, I mean, we've got certain things we all agree on, haven't we? I mean, yellow does seem to be one that most people agree on. I mean, I think the one aspect of yellow that I think people disagree about is, you know, those fluorescent vests that people have to wear sometimes, which to me are a really ghastly shade of greeny yellow, but very, very bright. Other than that, where some people think they're green, and funnily enough, one just went past the window as I said that on a bike. But you know, other than that, I think we all probably agree on yellow. So it's a bit of a, well, do feel free to tell me a counterexample. But it seems to me that it's the ones where people disagree about what the colour should be called, where we might be seeing something different. So, you know, to me, it's the colours like purple, blue, mauve, violet, magenta, those sorts of colours where it's really hard to agree. And I often, you know, I'm having a conversation where someone says, well, that's not purple, or that's not mauve, and someone else says, oh yes, it is. So that's the language thing is to me an indication that perceptions are differing. Where we're all agreeing about a word, that suggests to me that our perceptions are differing less. And I also think the fact we've got so few precise colour words might also be a sign we're seeing colours differently, you know, because in terms of single words for colours, there may be only about 10 or a dozen, aren't there? And other than that, we have to sort of use descriptive things like, you know, cobalt blue or something like that. Sort of rambling on. What else have we got here? Do you think different colour vocabularies in different languages reflect something biological or something cultural? Well, that's really interesting. I mean, I think probably both. I mean, the Japanese thing, it did make me wonder. I've been studying the Japanese language actually as well. It did make me wonder whether it's common in Japan to see a more bluey shade of green than here. And I don't know if a study's been done on that, but they've obviously felt a need for a word for blue-green rather than either blue or green. I mean, there must be ways of describing more precise shades in Japanese. I mean, I think there are cultural things as well. I mean, as a child, I thought the word mauve meant a sort of pale lilac colour, and then I found a lot of people thought it meant a sort of bright violet. But again, whether that's because people are seeing it differently or whether, you know, it's just a family tradition to use a different term, it's difficult. I think it's probably both. You know, if there's been a disagreement at some point about what mauve is, then somebody has started thinking, well, I may as well call this colour mauve because people don't seem to agree. And then someone else further down the line has a different view.
There's a new question in there. Why is paint pigment mixing different to light colour mixing?
Right, it's because it's sort of the opposite of the same process. So with light colours, you're mixing. When you mix them, you've got double the amount of light, so it gets brighter. Whereas with mixing paints, you're sort of it gets darker because you're loading more pigment in. So it's kind of the reverse. You're taking brightness out when you mix paint colours, and you're putting brightness in when you mix light colours. That's the simplest way I can put it, but it is slightly hard to explain, but they do turn out to be the reverse of each other. So I could show you with the digital mixing in a bit more detail. I don't think we've got time, but I do remember going to the Science Museum as a child in the days when it hadn't been sort of made all trendy, and seeing the 3 red, green and blue lights actually physically being shone over each other, and that they did make cyan, magenta and yellow. And I remember then thinking, well, why on earth is yellow so different from red and green if you mix red and green to make it? But that did prove that in fact that does happen. Of course, it's because red and green are close together and seeing similar colour wavelengths actually, and then when they overlap we see the yellow. I don't know if that quite answers it, but
oh, there's a controversial one there now. Is the modern version of the Cambridge light blue actually blue?
Oh, well, there we go. I think it could be a slightly muted form of aoi, as the Japanese colour is called. It's not a spectrum colour, is it? So it would be greyed out a little bit. According to that CIE system I mentioned earlier, which is the sort of standard way of referencing colour, I think you've got a sort of greying out, a sort of tonal quality in colour, and you've got saturation and you've got lightness. So the Cambridge blue is quite light, but it's also slightly greyed out, isn't it? Slightly muted. But other than that, the hue, the chromaticity of it, I would say is definitely the blue-green I've been talking about. What else have we got? There's so many things I like to say. So someone has got colour blindness in the family and differs between different members of the family. Oh, well, look, Lindsay, please do email me or get in touch. It'd be nice to talk about that some more. And if I do some further experiments, you know, I'm going to be looking for people to participate. And I might want 2 groups, you know, a group of people who either think they've got colour blindness and or they think they've got enhanced colour vision, and people who think they've got normal colour vision, you know, and it would be good to see what those different groups of people say. And I'd probably have a questionnaire where you self-assessed what your colour vision was like before you did the tests, you know, and then the test would be designed to pick up on some of the features I've been discussing in this talk.
I don't think we've got time to answer it now, but I put my question up, which we discussed while you were developing your presentation, which is, why have we evolved to see that part of the electromagnetic spectrum that we call visible light? And I've posted my attempt at an answer in the blog page. So if people want to read that and see how it relates to the surface temperature of the sun, I think that's quite an interesting discussion in its own right. So
definitely worth a read. It reminds me of that thing, you know, the anthropic principle about why we're here in the universe. I sort of feel it applies to our eyesight a bit as well. We've got this perfectly adapted eyesight to exactly what we need in this place under this sun, probably because we're on this planet under this sun. And I think evolution, you know, shouldn't be ignored. You know, this red-green colour blindness gene has survived evolution, which makes me think surely it must have some beneficial effect. And I think also, you know, one reason I wanted to use plants and minerals was because clearly over thousands of years we've evolved in harmony with being able to pick out what plants to interest us, what berries to pick, what flowers we like, and so on. And it would suggest to me that, you know, again, our eyesight had evolved, you know, in accordance with that to some extent, at least. I don't know if we've got time for anything.
Some of us are just seeing a message now saying that the time limit has been removed once again from our chat, so we can go on a few minutes longer if people want to.
That is beneficial, but I'm glad we've tried to stick to time. Did I think I missed one or two of the questions, did I? I didn't answer the one about paint mixing terribly clearly. I'll see if I can come back to that in a minute if I think of anything else to say about it. I mean, the other thing I was going to say was that, you know, obviously it's neurological as well, isn't it? It's not just about our retinas seeing, having cones that absorb these colours. Then the message goes through our optic nerve to our brain and we interpret it. And, you know, I've got synesthesia where I associate colour with numbers and letters. So all those sorts of things come into play as well. And so my idea about the rods absorbing green blue light, you know, that's partly perhaps a neurological thing. If I am doing that and other people are doing that, maybe we've just sort of almost trained our rods to sort of contribute to the information, the colour information we're taking in. But again, it's just a surmise or a conjecture, so it would need a scientific study to sort of verify that. But I'll look back at those answers on the quiz later, so that would be an interesting thing to do. I answered the one about the vocabularies. So I think I've probably answered them all. The one about the paints is the hardest really, but yeah, the subtractive, they're known as the additive and subtractive primaries. So magenta, cyan and yellow are, as I hinted at before or mentioned before, they're mixes of pairs of red and green, green and blue, blue and red. So if you take out one of those colours, you get back to the red, green and blue again. So they are sort of the inverse of each other. But everything I've done has been built around using these digital colours with three elements, red, green and blue. I've just realised I missed out of my talk a slide I had in the original version, which I wanted to show you. So if there's time, I might just briefly explain that I plotted my colours that I'd identified in my spectrum on a graph where I plotted the red, green and blue elements of them on this graph. And they looked quite similar to that graph I showed near the end with the curve for the rods in that part of the spectrum, and also the extra absorption of red at the violet end of the spectrum. So I wish I'd shown you that really. I don't know how I came to miss that one out. I might put that on the blog because that was a useful part of the talk.